So, Mr. Trice, would you tell us what we did after class ended the other day? You were wondering about a graph that was below the line of symmetry y equals x, and Cameron, you're the one that said that that's the equation of this line that Miss Jones drew and Miss Adams helped us define. This is the line y equals x. Everybody recognizes that line has slope of 1, goes through the point 0, 0, right? And all of these inverse functions are mirroring in symmetry around this same line. But Henry had a question, and he said, well, what if your graph was something like this, and we just took a piece of it, we didn't do the whole thing, but we took a piece of it, and he said, well, what about if this? Wouldn't it mirror like that and have a different line of symmetry? And what did we find?
It still flips, it's just the other side of the symmetry.
So what we found was that when we took all these points and flipped their x and y values, it looked like that. And it's still mirrored around the same line of symmetry. But you weren't 100% convinced at that point yet, were you?
It's pretty close. I didn't know what it is. I didn't know what else to... Yeah, I was just kind of thinking, I had a feeling that there was some type of line. Maybe I could travel across that line, but I don't know how to really...
Yeah, and we had some of those the other day too, right? I'm trying to think of what it looked like. I think your straight lines did that. I mean, we had one that did that, and the other one did this or something like that. You know, so we had a couple of those. The proof that every one-to-one function and its inverse goes around the line of symmetry. I'm only guessing, but it probably requires you to take first-degree equations, prove it, second-degree equations, and prove it. And if you want to try to prove it for any degree equation, I suspect it would get out of hand and be hard to do. And they may have accomplished it, but my guess is that you could prove it for first-degree, second-degree, third-degree, and fourth-degree would be a challenge, but you probably can do it. And I think beyond fourth degree, if you remember, there's no standard solution to higher than fourth degree equations. My suspicion is that it would be pretty hard to prove this for all degree equations, though maybe it's simpler than I'm making it out. And I think the end result is that you all want to think of it in terms of whatever the graph looks like. And Amanda, if the function you're dealing with is that a function?
Yeah.
Is it a one-to-one function?
No.
All right, so let me see if I can get a one-to-one function going here. Let me do it on the other board, because it's starting to get too messy over here. Let's make a complicated one-to-one function. I need to make it in such a way that it doesn't cross back over itself for a vertical line test, but it also can't cross back over anywhere to fail the horizontal line test. So maybe, and so if I go like this and turn it, it's going to fail the horizontal line test. So the only way I can get a one-to-one function not to do that is that I have to keep going up, even though it could change shape multiple times. It has to keep going up. You follow? Otherwise, if it turns down at any place, it's going to fail to be a one-to-one function. And then if it were going down, that's fine as long as it doesn't turn up. Bless you. So when you take every x and y value, and there's an infinite number of them, but take every x and y value and swap them, what are you going to get? You're going to get the mirror image of it around this line. Something like that. And every one-to-one function is going to have its line of symmetry y equals x. And it's by virtue of the fact that when you swap an xy value, wherever it is, whether it's positive, negative, whatever it is, when you swap it, what you're doing in essence is you're saying, look, if I went left this far, now I'm going to go down that far. And if I went up this far, now I'm going to go down that far. And it's always going to then take you on the other side of that y equals x line. Okay? So you all worked on graphing exponential functions and you got a feel for what they were like. Why can't we let the base be 1? Why can't we let the base be 1 with an exponential function, Rebecca?
Because then it would never change.
What would it always be?
Straight line. I'm trying to figure out which way to go.
So if our function was f of x equals 1 to the power of x squared minus 3x plus 2. That was my function, and I said x, sorry. And a is my base, but instead of we let the base be 1, then no matter what x is, what's the value of my function going to be?
1.
It's going to be 1. And so what is my resulting equation going to look like?
A horizontal line.
Through the point.
Y equals 1.
So everybody see that? If the base is 1, it doesn't matter. It doesn't matter. You're going to have 1 as a result. Now, you could, in theory, put something like 5 times this, but then what would you have? Every time you put in something for x, what are you going to get for this? 1, and then you're going to multiply it by 5. So all you've accomplished is to turn your equation into y equals 5. And so that's not a function that we really care about a whole lot because it doesn't really do a lot. And so that's why we're saying, look, your base can't be 1. What else can't your base be, Amanda? This was what you did for homework last night, 10.2, the first little bits that you did for homework. What else can't the base be?
It can't be like a square root.
Actually, it could be.
Oh, that's true. It can't be 0 because then it'd just be
Can't be 0 because then what would you get?
0 the whole time, so it'd be 1 dot.
Well, you could still let x be different things, and then for x equals 100, what would you get? 0 to the 100th power is 0. So you get the line y equals 0 if your base is 0. You'd get the x-axis, right? What else can't the base be, Cayman? Can't be 1, can't be 0. This is what you were learning about yesterday. What can't we have with exponential functions for the base? Not for x. We're not talking about domain yet. X can still be anything you want it to be, all real numbers. We're talking about the base. What can't the base be?
I don't remember.
Okay, Hannah?
Negative numbers?
Can't be negative numbers. Why can't the base be negative numbers?
Isn't that what we were proving on Monday? About like when we had the computer app with all the...
I don't think we did anything
Well, I mean like
with
about
that.
like how we could...
Maybe we did, and I'm not remembering it.
Let me see. If it's a negative number and you put it fractional exponent, that's not a real number.
Yeah, so if you have -3 as your base to the power of x, and it could be, you know, any form of a expression with x in it, right? But let's just keep the simple expression just x. And let's say we want x to be a half. Well, now we've got -3 to the half power, which, Henry, is the same as saying,
Square root of negative.
and where do we graph that on our number line, or our coordinate graphing? We can't. So, very good, Brogan. We can't have negative bases either. So another way of saying it is that your base has to be greater than 0, but it can't be 1. Okay? And once you do that, then you are in pretty good shape. Now, what happens if your base is greater than 1? What does your typical graph look like? Well, look at the bottom of page 617. This is your homework. Blue box number 2 at the bottom. Page 617, blue box number 2. This is part of what was assigned for homework for you to master for today. Sounds like I'm glad I didn't give you a quiz, or else you would have all been, I don't know what. If I had asked you on your quiz, if the base, what can't the base be? That would have been my first question. And you would have 3 possible answers, or maybe just put in x has to be greater, or a, sorry, the base has to be greater than 1 but not 0. But look at the second one. If the base is greater than 1, then the graph is going to rise from left to right. All right, let's look at that. When the base, should I plug in my computer to do it? It probably is faster. When the base is greater than 1, it's going to rise. So let's pick a number. What do you want to do with base? Let's pick 5 as our base. And again, we'll just use x because it's simple, but we could have like, you know, x minus 2, or we could have x squared plus 11, or any other expression with x in it as our exponent. Okay? So let's make a chart real quick. What happens if I let x equal -4? Am I allowed to do that, Gaiman?
Yes.
I am, because it's not that the x can't be negative, it's that the base can't be negative. Okay? So let x equal -4, and I get 5 to the -4th power. Henry, what does that mean?
1 over 5.
That's right, just the definition. And Brogan, is that a big number or a small number? Very small. So when I graph this, even when I get to just x equals -4, I've got a very small number. It's 1 over 625. I mean, it's even hard because my marker tip is bigger than I can differentiate such small numbers. Okay? What about when x equals -1? This is 1 over 625. What about when x equals -1? What does 5 to the -1st power mean, Brogan?
1 over 5.
It means 1 over 5, which is?
This -1, hold on, 0.2.
0.2. So it's still positive, but it's starting to climb a little bit. All right, how about when x equals 0, Rebecca?
That would be 0, right?
No, 5 to the power of 0
Oh, 1.
equals 1. Okay? So when x is 0, our graph is 1. Huh. All right? How about when x equals 2? Amanda?
Comes back.
That was easy. 1, 2, 25. And when x equals 3, Hannah?
125.
125. So you see, an exponential function is one that changes way more rapidly than just a normal first or even second degree equation, right? The rate of change is huge on this thing. So now I go through here, and then I go up like this, and man, I go up really fast. That's the typical shape of an exponential function. You should recognize that shape and be able to sort of conceptually have it in your head that when the base is bigger than 1, it's going to rise rapidly from left to right. And what will the value be when x equals 0? It will always be 1. Now again, you could, in theory, have something out in front of this, you know, like 4 times the quantity, 5 to the, and then you see that'll shift it. So don't let a shift mess you up. But in terms of just the base function, it's always going to go through the point 0, 1, unless you're shifting it in some way. Okay? Now, notice what it's doing on the left. Is it ever going to touch the x-axis getting over here? No. So what's its domain, Leah?
The order
All our numbers, what's its range?
from 0 or negative infinity to 0.
No, because negative infinity on the y-axis would be down here.
So it'll be from 0 to 1.
Good, and what do I put on left and right here for interval notation?
You do a brace and then a bracket.
So it's going to hit 0. It's never going to touch this axis.
Oh, right there.
It's going to get closer and closer to it, but it never touches it. So it has to be an open, not an open, but just a parenthesis. It's an open interval with a parenthesis to indicate that. So, Cayman, I noticed the other day you were struggling conceptually to get the, I'm looking to see, I have a ruler, to get the range in your head. Let me show you how to do range and domain. I'll use a pointer instead of a ruler. So, if you want to know the domain, take vertical lines starting from negative infinity, theoretically, and say, does this vertical line at x equals negative infinity, does it touch the graph anywhere? And in our case, if I keep drawing the graph, would this vertical line cut through the graph way over here? Then this x value is part of the domain. How about here? Here, 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 here. Is it crossing the graph? Is it crossing the graph? Will it keep crossing the graph? Until I never have to stop and it'll always cross there? Then that's why the domain is all real numbers. Now let's look for range. Turn it horizontal. And say, all right, let's start with negative infinity. Way down here. Does this horizontal line going through negative infinity, which isn't an actual number, but through very large negative numbers, does it cross the graph? Then this y value is not part of the range. How about here? How about here? Here, here. So none of these y values are part of the range, right? Negative 10, negative 5, negative 4, negative 3, negative 2, negative 1. Oh, but here's 0. Does it touch the graph at 0? And that was where we were trying to figure out that it doesn't ever touch. It gets closer and closer and closer and closer, but it never actually touches it here. But as soon as I move just a little bit north, so to speak, it now touches the graph. So the range starts just past 0, and that's how we indicate it in interval notation. Now, will all these y values touch the graph? So then it goes up to positive infinity for the range. So that might be helpful. You're not going to have a ruler, but you can just even take your hand and say, is it going to touch, is it going to touch? And if it does, it's included. And if it doesn't touch the graph, then that's not part of the domain for vertical or the range for horizontal. Okay? All right, well, what happens if your base is less than 1? Now remember, the base can't be negative. It has to be greater than 0. It can't be 1, but we just tested it for bigger than 1. What about when the base is positive, because that's required, but it's less than 1? Well, let's pick a number. Let's pick 1/5 as our base, and we'll raise it to the power of x just for simplicity. We'll make a chart. Okay, we'll have x and f of x, and we'll put in x equals 0. Rebecca, what is 1/5 to the power of 0?
1.
Oh, look at that. It goes through the same point that we had when our base was greater than 1. So do you think our graph is going to look like this then? Because that's the basic exponential graph. Well, let's see what happens. Let's let x be negative 4, like we did before. 1, 2, 3, 4. 1/5 to the power of negative 4. Brogan, what's that equal to? Oh, you're doing a little trick here. I can't remember all those rules. All I know is what a negative exponent means. So it means 1 over 1/5 to the 4th, which equals 1 over, apply the exponent to the numerator, 1 to the 4th over 5 to the 4th. Dividing by a fraction is the same as multiplying by its reciprocal, and so I get 5 to the 4th. Is that what you said? So he knew it faster and better and easier because he knew how to manipulate a negative exponent with a fraction. I couldn't remember those rules, so I just applied the meaning of the negative exponent. Okay? What is 5 to the 4th? 625. Remember we did it over. 5 times 5 is 25. 5 times 5 is 25. 25 times 25 is 625. Do you know all your squares up to 25, Cameron? I don't know them past 25. You know 1 squared. 2 squared? Say it.
Like
What's 2 squared?
4,
3 squared? 4 squared? 5 squared? 6 squared? 7? 8? 9? 10? You all can do that, right? Let's see how far you can get. 11? 12? 13? Very good. 14. Flip the last 2 digits. Good. 15. Very good. Could you all do up to 15? Some of you can. 16. 256. 17.
289.
Very good. 18. 324. Anybody got that one? 18. 19. 381. 20. 400. That's an easy one, right? Now, between 20 and 25, I'm a little rusty, but 25 is 625, so 20 squared is 400, 25 squared is 625, so we got to get from 400 to 625. 21 squared 441 maybe or something like that. You gotta do it for me.
Yeah, that's right.
441. And then 22 squared is 464. 484. 23 squared. 460 plus 49. 509. What did I miss? 529. 24 is what? 596 or something like that? 576, and then 25 is 625. All right. So, what did we say it was, Brian? -4 was huge, wasn't it? Is that what you told me?
Yes.
Wow. All right. So -4 is so high I can't even reach it. So let's do a smaller one. -2 would be 25, which is way up here. -1 would be 5. Okay. And it goes through here. Goes up forever. All right. How about 1? 1, where are we at? 1, what's our original function? 1/5 to the power of x? Is that what we're doing? So what is 1/5 to the power of 1? 0.2. And then what do you think is going to happen when I square 0.2? It's going to get bigger or smaller? It's going to get progressively smaller. So how would you describe this, Anna?
Any base that is less than 1 but greater than 0 goes from left to right, from up to down.
Good, good. And the domain, Hannah, would be?
Negative, positive.
Good, otherwise known as all real numbers.
Oh, yeah.
And what would the range of this one be? Yeah.
Maybe 0 to positive, or negative, or negative.
Look at the range. What are the y values doing? Are they going to negative infinity?
Probably. No, they're going up.
The y values are allowed to be all the way up to positive infinity. Does this y value appear on the graph? This one, this one, this one, this one. Where do the y values stop appearing? 0. So from left to right, it goes from positive infinity to 0 from left to right. We don't write intervals from left to right on the graph. The y values go from positive infinity down to 0, but we don't write intervals this way. We write them in their number line order, and so we write the interval the same as we wrote the other interval. It has the same domain and range. But you can see they're two very different graphs, even though they have the same domain and the same range. Okay?
Will it always be that way? They have the same domain, same range?
Will what always be that way?
Like for the exponential.
Well, if you shifted them, then the answer would be no. So let me ask you this, Henry. Could I write an exponential equation like this? F of x equals -2 times the quantity 5 to the power of x. Is that allowed? So what would I end up with? Well, here's my graph for 5 to the power of x. All I got to do is take every one of my x values, and to get the function value, start with what I got as my function value originally, and multiply by -2. What would that look like, do you think?
I guess you're inversing. No, you're flipping. You're flipping your graph, right? It's gonna
So at this point, what is it going to be?
um,
This is negative. This is the point 0, 1.
0, 1 from 0, -1.
Not -1, but
Oh, sorry.
multiplied by -2, so it'd be down here. All right, and then do you remember anybody when we did 1? I don't think we did 1. When we did 1, we got 5, supposedly. So what are we going to get down here? We're going to get -10. When we did 2, we got 25. So now we're going to have -50. So it's going to move even faster now, so to speak. Okay. And then how about here? When I get really close to 0 came in, really close to 0, but it's still positive, and I now multiply it by -2. What am I going to get when I get a number really close to 0 and multiply it by -2?
It will get smaller.
It is. It's also going to be close to 0. So it is also going to get close here, but it's going to open up faster than this one is opening toward the up. This one will open up faster. So you'll get this graph here. So Miss Lindsay, to answer your question, will they always have the same domain and range? The answer is no, because it really depends on what your function is. And you can see that the base function will always have that domain and range, but the actual function could have its own, all sorts of things. And then could I do all this, guys, and then add 10 when I'm done? What do you think that's going to do, Leah?
It's gonna shift it over to the left, or to the right.
So remember what we're doing now, put brackets here, like this, and say whatever I get, let me back up. Here was my original one, 5 to the power of x. That was this top one. Now, whatever we got at any point, we're going to multiply it by -2. Okay, that gave us this bottom one. Now, whatever I get, which is this bottom one, for every point I get, whatever I get, I'm just going to add 10 to it. And so just adding 10 means you're going to move everything up by 10. Now, of course, if your number down here is -25, then adding 10 will bring you up to -15, so that your graph will go kind of like this and go through there. And you'd have to figure out, like here, it's going to go through the point 11. I don't know if I drew it right, but it probably goes up a little higher. But just going to shift it up. So the easiest shifts, Brogan, are the add or subtract the number when you're all done evaluating your x. Like when the whole thing's done, add or subtract the number, it just shifts it up or down. The left-right shifts, Leah, are what happens when you add or subtract something to x before doing any operations. And then that'll shift it left and right. All right? All right, let's keep moving. You know what's waiting for you, don't you? Logarithms. All right, so example 3, graphing a more complicated one, and so they showed you that. Now, down at the bottom of page 618, they give us a property for solving an exponential equation. So Rebecca, you tried to solve an exponential equation, you ran into trouble, but look, we have a property here that might help us. There's only one problem. The problem I gave you wouldn't be helped by this property. But it's a good starting place. So what happens if I give you a problem like this? 5 to the 7th power equals 5 to the power of x. Can anyone of you figure out what x is if I gave you this problem? What is x?
7.
How in the world did you guys figure it out? You haven't even learned the property yet. It was pretty straightforward, right? It's just intuitive almost to say, well, 5 to a certain power equals 5 to what power? And you're like, 7? You don't need a property, but let's go ahead and describe a property so that we can use it when it's harder than this, okay? And the property is, if you have the same base, an equation where each side is the same base, not that it includes the same base, because what if this were like, x plus 11 minus 5 to the 7th power? You can't use this property in that case. It has to be each side is just a base raised to a power. And if so, and the same base is on each side, then you can set the exponents equal. Okay? And solve the resulting equation. So let's take a look. In example 4, we've got the equation 9 to the power of x equals 27. So Brogan, we take a look at that, and we say to ourselves, well, what good does our property do because we don't have the same base on each side? But you say to yourself, wait a second, maybe I can do something. By the way, what's the exponent on the right side, Brogan?
Just 1.
Just 1. And so you're like, I can't say x equals 1 because I don't have the same base. But could I convert 9 into something else exponential?
Turn to 3 squared.
3 squared raised to the power of x. So Rebecca, I'm going to need your help there on the left side. Brogan on the right side? 3 cubed. So now you're like, oh, I've got the same base, so does x equal 3? Hold on. You're not raising 3 to the power of x on the left side. You're raising 3 squared to the power of x. You don't have the same base yet. All you've done is converted this 9 into 3 squared. You don't have the same base yet. But we can use the rules of exponents to do what to these?
Multiply them together.
Because we have a power of a power And now do I have the same base on each side?
Yeah.
So what do they call the rule, by the way? Do they call it a property for solving? They gotta give it a better name than that. Let's call it the exponential equation property. I don't know. But we need to give it a name, okay? So what do we do, Rebecca?
We set them equal, so 2x equals 3.
Good, and then we solve for x, so x equals,
3 over 2.
and Cayman, we all make mistakes, and so check it. Does 9 to the power of 3 halves equal 27? Well, Henry, what does this mean?
Yeah, if you're taking the cube root of 9 squared.
Uh-uh.
Taking the square root of 9.
Square roots. The bottom is your root. What is the square root of 9?
3.
Raised to this power, and is 3 cubed equal to 27? Then it checks out. So the square root of 9 isn't negative 3?
No, sir.
It's not, because when we say square root, we mean the principal or positive or natural square root, unless it says plus or minus. And we introduce plus or minus when we introduce the square root. We didn't introduce the square root, we were just evaluating the exponent, so we don't have to do anything like that. Okay? So for homework, you can do the rest of 10.2. All right? On to 10.3. And guess what 10.3 is? Logarithms. All right. Notice that if you take the exponential equation 2 to the power of x, you get the blue line at the top of page 625. And Matt and Natalie, if you're listening to this, get your books out. Page 625, top of that page. Look at the blue graph. It's the graph of the exponential function y equals 2 to the power of x, just like you already did in this previous section. Okay? Is that a one-to-one function, the blue one?
Yes.
How do you know?
Because it passes the test.
It passes both horizontal and vertical line tests. So does it have an inverse, Henry?
Yes, sir.
Where is its inverse going to mirror around?
Why was that?
You sure?
Yes, sir.
All right. So let's go ahead and draw that inverse by just plotting points, Rebecca. So we'll just find points on the exponential blue one, and then we'll do what to those values to get the inverse?
Switch.
Switch them around, and then plot those points, and we get the red line. We didn't do anything, Brogan. We just reversed the points to get it, okay? What's the equation of that red line? The answer, we have no idea. Well, let's see if we can't figure it out. And this is the problem I gave to Rebecca the other day. So let's go ahead and figure it out, Rebecca. Y equals 2 to the power of x. We want to take the inverse. So what do we do, Leah? If we want to find the inverse of a function? Switch it around like this. And that's our equation. Ta-da! But what's the problem?
You haven't solved for y.
Well, who says I have to solve for y? That's the proper way of doing it, right? Because in order to say f of x equals whatever, you got to solve for y and then substitute f of x for y. And I haven't done that. Okay, so here's an idea. If the base on this side were 2, then we could use our exponential, what do we call it? Equation property. So if this were 2, I'd be good to go. It's not 2. Okay, so what Rebecca said was, well, if this were like 3, if y were 3, I could take the third root of both sides. So Rebecca said, well, I'm going to take the yth root of both sides. And then she said, that's true,
That doesn't help.
but it didn't help. Okay, so let's go back again and say, is there any way to convert this into a base of 2? Because if there is, then I'd be good to go, right? So, but the problem is x is a variable and it can change all the time. So like if x were 4, could I change it into base of 2? If x were 4, could I change it into base of 2?
yes.
What would it be? 2 squared. So what would y be if x were, what did I say, 4?
2.
Y would be 2, because 2 squared is 4. What, Brogan, what if x were 8? Could I change that into a base of 2? And it would be what? It would be 2 cubed, so y would be 3. So by the way, if let's just do like this, x and f of x, and this is actually the inverse function of x, right? So we said this would be 2, this would be 3. What if x were 16?
4.
It would be 4. You see the pattern yet? What if x were 32?
5.
It would be 5. What if x were 2?
1.
What if x were 1? Y would be
0.
0, because 2 to the power 0 is 1, so if x is 1, y would be 0. What if x were negative? 2 to what power, Amanda, would give me a negative number?
No.
That doesn't exist, does it? So x is allowed to be 0, but x can't be negative. Okay, so tuck that in the back of your mind. All right, well, we could graph this, and we would get the red line that's in your book. Okay? And notice, by the way, x goes down, 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 down. They actually, I'm going to make sure I did this right because it doesn't look, oh no, x can be 1. Sorry, x can be 1 and y can be 0. Can x be less than 1? It can be. It gets harder though. What if I let x, here, I'll do like this. I'll make it all the way up to here, x and inverse of x. What if x is a half? Anyone figure that one out? What is y going to be if x is a half? How do we convert, if x is a half, how do we convert that into a base of 2?
Oh, you would do it to the negative.
2 to the negative first power equals 2 to the y, so y equals, okay, what if x were 1/8? How do I convert this into a base of 2? 2 to the negative third equals 2 to the y, so y equals, okay, so you see what's happening? And that's where you get your red graph from. Everybody see that?
Mm-hmm.
All right. So, what we have, does everybody agree? Where's my red marker? What we have is a function that is an exponential function because it contains an exponent? No. Why is it called an exponential function?
Because the variable is the exponent.
Because the variable is in the exponent, okay? It has a variable with an exponent. We can find the inverse of that pretty easily, and we can plot points based on that equation pretty easily, right? But the problem is, what if I pick a number in between, like remember 4 gave us 2 and 8 gave us 3. What if I pick a number in between there, like 6? 6. Well, then I want to know 6, I'm doing the inverse equation, 6 equals 2 to what power? So take your calculators, and you all have a button on your calculator, right? That you can say 2 and then hit like y to the x or whatever it is, and find me a number that when you take 2 to that power will give you 6. 2 raised to what power gives you 6?
It's in between 2.6 and 2.5.
Oh, between 2.5 and 2.6. That's not exact enough. Keep going. Give me in between hundredths.
It's greater than 0.55.
So greater than 2.55, but less than 2.56?
Mm-hmm.
Is that right? It's not exact enough.
No,
No?
it's greater than 2.56.
It's greater than 2.56?
Mm-hmm.
Is it greater than 2.57?
Oh boy.
No.
Okay, so it's between 2.56 and 2.57. It's not exact enough. Get it to thousandths. Raise 2 to the power of 2.565. Henry, what do you get?
I see an overflow error.
An overflow error. So you can't, on your calculator, raise 2 to the power of 2.565? What kind of calculator is that?
Wait, hang on.
2 raised to the power of 2.565.
2.565. Okay, I get 5.9175.
Okay, so it's bigger than this, so let's try 2.568.
It's 2.59, I think it's closest.
569? What this,
Oh wow, that's crazy. It's 5.933. 2.569.
2.569 gives you what?
5.933.
So that's still too small. All right. So 2.569 is too small, but 2.600 is too big?
Mhm.
Is that what you told me?
No, that was wrong.
Oh, all right. All right, now we got more work to do. Come on, let's figure it out. Let's go back to tenths again since 2.5.
2.5, it's in between, or I put 2.589, and I got 6.01.
Okay.
So that's a little bit above.
I got, when I raised 2 to 2.571, I got 5.94.
Okay, so that one is closer. So it's between these two numbers, guys, but we would like it to be somebody do 2.58 for me, please. What do you get?
5.9.
So it's still too small? All right, so it's between 2.58 and 2.59. Okay, so Henry, can you check 2.585 for me?
That's 6.00.
So that's too big, so it's less than 2.585, but bigger than 2.580. So somebody do 2.583.
I think
It's
the
5.99.
So 2.583 is too small, so now we got it down. Somebody do 2.584.
5.9959.
All right, so it's bigger than that, so there we go. It is, if you raise 2 to a certain power, we don't know the exact answer, but if you raise the number 2 to the power of 2.584 something, but not as big as 585, you will get exactly 6. So when x is 6, what will y be? 2.584 something, but less than 2.585. Okay? So Henry, we can solve this equation. We can solve this equation by making a chart and plotting the points. And we can plot the points by just trial and erroring what the exponent needs to be for each x value. In this case, we chose 6 for x, right? We just need to trial and error it to get a value for y that'll make my base of 2 raised to that power of y equal to 6. We can do that, and we can get as exact as we want, because if I asked you to go to the millionths place, you could just keep working and eventually get it, couldn't you? So we can get as exact as we want, we just don't know the exact answer yet, like in an equation form. We just know that we can make it work in a chart. Okay?
Mhm.
So, Rebecca, the answer to the problem I gave you the other day is, I'll make a chart and plot the points, Mr. McGowan. But I asked you for an equation, and you said, I can't do an equation unless I can take the y root of both sides. What if I tell you that you can take the y root of both sides using a new terminology that doesn't really do anything except what we were just doing with our calculators? It's going to represent all the work that you did on your calculator. Okay? And we're going to call it a logarithm. Now, of all the things I'm about to say, Matt and Natalie, are you awake? Of all the things I'm about to say, this is the most important. Logarithms are hard for students. They're hard for teachers. Logarithms are hard to get your head around. This is the most important thing I'm going to say. Today, tomorrow, or next week. A logarithm is an exponent. That's it. If you can get your head around that, Keenan, you'll get logarithms faster and easier. It's hard to get your head around. A logarithm is just an exponent. That's all it is. Okay? A logarithm is an exponent. Now, let's say that I take this equation that we would like to solve for y, and I say to you, I'm going to solve it for y. I'm going to say that y equals the exponent we need to find on, or how do I say it? Like I'm raising 2 to that exponent. It's the exponent we need to find and raise 2 to that power, namely the y value that we get. It's the exponent that we need to find and raise 2 to that exponent power to give me my chosen x value. I just solved it. You like it? I just solved it. I just told you what y equals. Y equals the exponent that I need to raise 2 to give me whatever my x value is. There it is. I just solved it for you. You impressed? And now I'm going to call the exponent that we need to find and raise 2 to that power to give me my chosen x value. I'm going to call this whole thing a logarithm. You see what a cheesy, cheap game we're playing here? All I'm doing is giving this thing a name. I'm not doing anything. I'm just giving it a name. We've done that in math before, haven't we? We've just given stuff names and said, like what's the square root of -1? Oh, has that like expanded your world and made you like smarter? You're like, well, no, we just called something we didn't understand by a letter. It might make us look smarter, but it didn't actually do anything. I just substituted I for square root of -1. It didn't do anything. But actually later on, it helped us, didn't it? Now, if you had left it as square root of -1, you still could have done all the things we learned later. But it's just a little bit more convenient than writing square root of -1 all the time. We'll just call it I and it makes our life easier. Well, do you want me to say this every time we have a problem with an exponent that we can't solve? No. But how about if I call it a logarithm? Is that going to be helpful? Well, actually, it'll sort of shorthand it for us, and it'll be helpful later. But for right now, Brogan, and this is what they don't tell you when you go to college. They often will pull these tricks. And they'll be like, oh, we're going to call it, and they give you a name like, we're going to call it a differential equation. And you're like, wait, what is this stuff? And in reality, maybe they just gave something a name. They didn't really do anything. They just gave it a name. And then they'll give it a symbol. And all you're doing is learning their language. It's like, all right, well, you renamed it and you gave it a symbol, but you really haven't done anything with it yet. Well, don't get tripped up at the first step, which is just naming it. Later on, they'll do stuff with it that might trip you up. But at least for the first step, Leah, make sure you understand that they're just naming it. They're just giving it a name. So what if I rewrite this? It's starting to get sloppy over here, but I think you guys can follow me. What if I rewrite this equation as y equals the exponent that I need to find and raise 2 to that power to give me the indicated value of x? What if I say, I'm going to call that the logarithm with base 2, so remember, logarithm means the exponent that I need with base of 2 that will give me x. So I've just begun to shorten this. Did you all understand what this meant? It just meant like we did when we let x equals 6. We said, hey, what power on 2 will give me x equals 6. We took our calculators out and we kept narrowing it down. And we said, oh, the exponent we need with with our base of 2 to give me x equals 6 is 2.584 something.
So it's kind of like logarithm is like almost like x, like it's just a variable.
It's not x, but it is a changing value, yes. So in that sense, it's like x, but it's not x. But it is the exponent that you need on a certain base, in our case 2, to give me whatever my changing x value is. We're just going to keep recalculating what exponent we need to make it work. Because, Henry, if we can turn this into a base of 2, then we can say that y equals whatever number I raised 2 to that power will give me what y is, and that's saying the same thing as this. All right, so I got y equals a logarithm, it's just the exponent, with a base of 2 that will give me the value of x. So I'm going to shorthand this some more, and I'm going to say it's going to be the logarithm with a base of 2 that gives me x. I'm just shorthanding it. You see what I've done? The logarithm, which means the exponent that I put on the base of 2, what exponent do I need with a base of 2 that will give me x? I just shorthanded it, Henry. That's all I've done. And then I'm going to shorthand it one more time and just abbreviate logarithm as log base 2 of x. All I did was just rewrite it. I just wrote the same thing that I did here. I wrote it here and here and here. You're now learning the language of logarithms. There's nothing new here. There's nothing different. There's nothing helpful yet. It's just symbolism. It's grammar. Okay, you're learning the grammar of logarithms. Okay? So, Henry, let's review. Exponential equation. I want to find the inverse. I trade out x and y, I get an equation I don't know how to solve. Though I look at it and say, well, if I have a certain x value, if I can figure out what exponent on my base will give me that x value, then I've solved it for y. And so we did that with our calculators. But now what if I change the x value and say, what exponent do I need if I change x to 10? Well, now you need to get your calculators back out and say, what exponent on 2 raised to that power will give me 10? And you're going to do that for every x value. Sounds like a lot of work. Okay? Well, if I can shorthand it, I can write it this way. What exponent, that's what a logarithm is, what exponent do I need on the base of 2 for each x value? So keep plugging in x values and answering the question, what exponent on 2 do I need to give me that x value? That's what y is going to equal. That's your function value at that moment. Okay? Welcome to logarithms. What's a logarithm, Leah?
What's next one?
What's the base in this equation?
2.
And what will I get when I raise 2 to the power of whatever I get for y? What will my answer be?
X.
X. So I could rewrite this as base 2. What's my exponent? Y is my exponent. What's my answer? Well, when I raise 2 to that y value, what's my answer here?
Oh, x.
X. These are the same thing. So, Rebecca, you want to solve that? I don't remember the equation. You want to solve it? Write it in log form. You're like, but it didn't do anything. It's just the same equation written with y equals, but you fudged it by just making up a word called logarithms to mean the exponent on a base of 2. You didn't tell me anything new than what we had when it was in exponential form. You're right. You're absolutely right. It looks nice though, doesn't it?
Did someone just make up that word and then all the math people agree that it was fine?
Yes. Historically, the guy who did a lot of logarithms, the name is escaping me, but he just played around with it for a while and realized that there's some advantages to it. But then, lo and behold, he started exploring some of the properties of the inverse of the exponential function. And of course, you would expect that the properties would mirror the exponential function's properties, which had been long studied. And so it really was almost an easy thing in the sense that all he's doing is now taking the inverse of things that we already had previously. And it became very useful.
It sort of feels like when we introduce, it's almost just like where we can't figure out how to solve these equations, so we're entering an imaginary world and creating new math
That's exactly right.
principles.
That's exactly right. And if that only led us to the same things that we started with, then it really wouldn't amount to much. But the reason that it's part of mathematical history is because it turns out that it's incredibly helpful, just the way all these functions and equations are helpful in real-world applications. we're running out of time, so let me just say it to you. The real world applications that are especially helpful are really big numbers and really small numbers. And do you think the Greeks cared about like huge numbers? Not a whole lot. Do you think the Greeks cared about like atomic level small numbers? Not a whole lot. Do you think the Greeks did much with exponents and logarithms? Not a whole lot. Why? Because they didn't need them. But then when we started thinking about traveling to the moon or sending us an explorer out to get all the way to the outer edge of our solar system, and we started discovering DNA and all that, do you think we needed to talk about really big and really small numbers and manipulate them in ways that were helpful? And do you think the scientists who computed these things, by the way, Hidden Figures is a movie that's been recommended to us. I haven't seen it yet, but do you think they wanted to write all those zeros if it was a big number, or all the zeros after the decimal point if it was a small number, and sit there and be like, all right, you need 63 of these, you ready? Okay, now, and then they write it out, and they're like, now multiply that by, 62 zeros with 643 at the end. You think they want to write all those numbers out every time? You can see why logarithms and exponents would be, which logarithms are exponents. You can see why exponents would be helpful for both big and small numbers. Okay? So, 2.5 minutes. Logarithms, all you need to do is understand the meaning of logarithms. If you understand the meaning of logarithms, then look at example 1a. Can you write that in exponential form, Henry? Example 1a. Well, what's the base? 4. Raised to what power? Now remember, y is the power. So what is this equation solved for? It's solved for a number, so that number is your y value. So 4 raised to the power of -2 is going to equal x. Now, that's going to twist your melon, but practice that for homework. Okay? Now, look at example C. Rebecca, what's our base?
X.
What's our power?
2.
And what is it going to equal when we take x to the power of 2?
3.
And then solve. Okay, one more. Mr. Ecton, what's our base for D?
49.
What's our power? What's our result?
The cube root
Now, when we write that, we're like, now how do we solve this? A lot of help that was. Wait a second, can we write 49 as a power of 7? We can, 7 squared. Can we use the power rule of exponents to multiply 2 times x? We can. Now we've got an equation with 2 bases that are the same. What can we do? We can use the exponential equation property and set 2x equal to 1/3, solve for x equals 1/6, etc. Okay? So I want you for homework to do up through example 2. So you got the rest of 10.2, okay? And then I want you to do 1 through 40, which is all about just converting back and forth between logarithmic and exponential, and just get used to that. Question?
Oh, yeah, logarithm button on our calculator, are we gonna learn what we use that for?
Yes.
Okay, I didn't know if we were supposed to use it now.
Yes. Yeah, at this point you don't need it, but you're going to learn it soon enough. All right, you're dismissed.